Hello and welcome to the review for the first test or the midterm in INEN 2373. What I'm going to do is work one problem from each chapter as an example because your test will actually have one problem from each of chapters 1 through 6. The problems from chapters 1 and 2 will be very short, and they're going to be 10 points each, and the problems from chapters 3 through 6 will be 20 points each. So it'll be a 100-point test, and it counts as 20% of your total final grade. So it's very important that you view this video. There will also be a practice test so you can get used to the format and the administration of the test. I recommend strongly that you take that practice test as well after you have reviewed this video and the accompanying notes that I will post with the video as I do with the lectures. So I'm going to read the question. I'm going to draw the cash flow diagram. I'm going to go through this 3 steps of putting on the general formula, then the specific numbers for the formula, and then finally the answer. And that's the way I want you to work problems on the test, and you'll be handing in all of your work. So be sure that you've done all of the steps that I am doing in this example review for the test. So question 1 says you borrowed $20,000 and 3 months later you repaid the lender $21,200. So your cash flow would look like this. You received 20,000, and if these are months, 1, 2, 3, you had to pay back 21,200. So that is the cash flow diagram from your perspective. The lenders, of course, would just be the opposite in terms of the relationship. Your payment included both principal and interest, and so this is both principal plus the interest on the loan. So the principal was $20,000. We know what that is. So by knowing that, we know that the interest then is equal to what you paid back, which we'll call F3 here. That's the future value at time 3. And these are months. Will be the F3 minus what you started with, which was the $20,000. So F3, that's the interest, and that is going to be $21,200 minus $20,000, which is what you started with. So your interest, which you could have probably done just mentally in your head, was $1,200. And from simple interest formulas, we know that the simple interest is obtained from what I called the PIN formula, P-I-N, where I is the simple interest rate in this case. That's only true in chapter 1. The remainder of the chapter, I stands for the effective interest rate in all of our compound interest formulas. But in the simple interest formula, it also stands for the simple interest rate. So I is equal to 20,000, that's the original principal, times the interest rate, which we're trying to solve for, times the number of periods. And it says the annual interest rate, so we'll put N as the number of years. Well, 3 months is 1 calendar quarter, so it's 25% of a year. So that would be times 0.25 years. And that is equal to $1,200. So now we have 20,000 times I times 1/4 or 0.25 equals 1,200. So if we multiply the 0.25 times the 20,000, we will get 5,000. I is equal to 1,200. And now if we divide both sides through by 5,000, we'll get I is equal to, and this is I annual because this is the number of years here. So it's going to be equal to 1,200 divided by 5,000, which is equal to 0.24, or I equals 24% per year. Simple. Interest. And that concludes problem 1. And I'm going to go on then and work another problem for you. That's a problem from chapter 1. So I'll go on and work a problem from chapter 2 next. And that problem is now up here on the video. And it says, so I'm going through all the steps now, drawing the cash flow diagram, using the general formula, and then plugging in numbers and so on. An engineer got a late start planning for retirement. She will place 15% of her salary each year into a stock fund. So she's going to invest this money, 15% of her salary. If her salary this year, this is year 1, her salary is $100,000, and she expects her salary to increase by 5% per year, each year, determine the future worth of the retirement. So she's always putting in 15% of her salary, but her salary is increasing at 5%. You can see right away that is going to be a geometric series. And because it's increasing by a percentage or a fractional amount. Determine the future worth of the retirement fund after 15 years, provided it earns 10% per year. So now we've got a lot of percentages here, so let's keep them all straight. This is the rate of return on her investments. So now to get the general formula for a geometric formula for the future value, future worth of a geometric series, first of all, let's draw this thing up. Okay. She's earning $100,000 and she's putting 15% of that. So that's $15,000. That's going into the account the first year. So we call that A1 in our geometric series calculations. And then this is going up by 5% a year. So the second year, this would be A2 would be equal to 15,000 times 1.05 to the 1 power, and so on. And this will go on for how many years? At the end of each year, she expects her salary to be worth 15. For 15 years. Okay, so in year 15, the amount she'll be putting in, that will be A15, would be 15,000. We don't really need to know this number because it's all taken care of in the formula, to the 14th power. Why? Because the first one was to the 0 power, not the 1 power, and the second one is to the 1 power. So that's the way it works. Now what we want to know, F. So we're given A1 is $15,000. We got that by multiplying the 15% times the 100,000. We're given that this series is increasing at the rate of 5% per year. We're given that these funds that are going into this are earning 10% per year, and we're given that there's 15 years of deposits between now and the future. So the generic formula is F is equal to A1, find F given A1 at interest rate I at increasing geometric series rate G for n periods. That's the generic formula. The specific values are 15,000 for A1, find F given A1, I is 10%, G is 5%, put 5% there, and N is 15 years. So then the future value of that I can get from the Engineering Economics Career app, which I'll take out my phone and go to Engineering Economics Career app. I go down here to F given A1 at the very bottom. It has a J there. The developer of the app used J for the increasing rate of the series. The textbook used a little G. So now it asks me for the interest rate. That's the first thing I need to enter, which is 10%. Then it asks me for the rate of growth in the series, and that's 5%. That happens to be already in my calculator. And then it asked me for the number of years, and I will put in 15. And then it asked me for the first term in series, the A1, and that's 15,000. And then I'll tell it to calculate the number for me. And the number comes out to be $629,496. The next problem I'm going to work is a problem from chapter 3, and it says specialty parts cost will increase by $5,000 every 3 months. So we right away, if you've worked enough problems, you'll realize, okay, something is increasing by a constant amount. That is an arithmetic gradient series indicator, so to speak. If the cost for the first quarter is expected to be $100,000, now we know an arithmetic gradient series must start at 0, so this must be some sort of a combined series, but I'll read on. What is the present worth of the cost for a 3-year time period at a MAR of 16% per year compounded quarterly? So again, I'm going to start by drawing a cash flow diagram. So I get everything straight. We've got a 3-year period, but we've got a quarter. At the end of one quarter, we make a deposit of $100,000. And then every quarter after that, it increases by $5,000. So the next one will be $100,000, $105,000, and the next one 110, and so on and so forth. This is 105, and so forth. Now this is going to be year 1 because there's 4 quarters in a year, right? And then, you know, if we filled in all of these, I'm going to just go back over to the end of year 3. How many quarters are there in 3 years? Well, there's 12 quarters, right? Four times 3. And so there'll be a certain cash flow in every one of those quarters. We don't have to really know how much that is. But what we end up here, if you look at this cash flow, you have a uniform series of $100,000. I made a video one time, and I remember this, that I broke this series down into two series, a uniform series of $100,000, not the same numbers, but 2 and so on, up to 12. And then I had a gradient series, an arithmetic gradient series of $5,000. So the first payment in an arithmetic gradient is always 0. The next payment is 5,000, and the next payment will be 5,000 more, or 10,000, and so on out to the 12th payment. The 12th payment will actually be 11 times 5,000. It'll be 55,000 if I did my math right. But I don't really have to know that. I just have to know that I have these two kinds of series. I have an interest rate of 16% per year compounded quarterly. Well, all of the cash flows are quarterly, so I must find the quarterly interest rate. So let me do that over here. I quarterly, using the effective interest rate formula, is equal to 1 plus R quarterly over M to the M power minus 1. You should know this formula from the chapter 3. R quarterly, remember, you can convert from R annual, this is R annual right here, to R quarterly just by dividing it by 4. So this would be 1 plus 0.04, 16 divided by 4, to the 1 divided by 1, because it's compounded quarterly. So this is the rate per quarter. This is the number of compounds in a quarter. And this ends up just being 0.04, which is 4%. So now we have a rate. This is percent per quarter. Quarterly, QTLY. Okay. So now we want to find what's the present worth of all of this stuff. Well, this is the uniform series. This is the arithmetic gradient. So the present worth at 4% is equal to, well, starting with the uniform series, it's A, P given A, I, N. And then you've got an arithmetic gradient, G, P given G, I, N. That's the generic formula. Then we're going to plug in the values. Present worth at 4% is equal to, A is 100,000, P given A, 4% for 12 quarters. There's 12 of these, okay? Plus G, well, G is $5,000, P given G, 4% for 12 quarters also. And now we just plug into our, go get the number from the from your app, or that's what I prefer to do. If you do that, you'll get, this will be 100,000 times P given A for 12 quarters, and that's 938,000, sorry, $507. And then if you go to your app, plug in for this number, you get 236,239. And then if you add those two together, you'll get 1,174,746. And so this is your final answer to problem 3 that's asking you what is the present worth of these 12 quarterly payments that start at $100,000 and go up actually to $155,000. And that covers the problem from chapter 3. In this problem from chapter 4, this is the fourth example problem that I'm working for you. Again, I'll read the question, draw the cash flow diagram, put in the generic formulas, and then we'll crank out the numbers. A company must decide between two alternatives. Alternative A has an initial cost of $155,000, whereas alternative B will cost $210,000. Alternative A will cost $30,000 per year to operate, and alternative B will cost $10,000 per year. So alternative A costs less to buy but more to operate. Alternative B costs more to buy but less to operate. That's a very common type of decision-making situation in many kinds of purchases. What is the present worth of each alternative if the study period is 30 years and the MAR is 10% per year compounded annually? So we're going to start with drawing a cash flow diagram. Let's do the cash flow of A to start with. It costs $155,000. And then $30,000 every year to operate. And then that goes out to 30 years. So alternative B costs $210,000. But only $10,000 a year to operate. So that's the cash flow for alternative B. And now we want to find the present worth at 10%. So the present worth of A at rate I, or at the MAR, this is the generic formula now, is equal to the initial cost, P, plus the annual operating cost, A, P given A, I, N. And this will be equal to minus 155,000, that's the initial cost, and minus 30,000, that's the A value. P given A, 10% for 30 years. So the present worth of A at rate I, at 10%, now we'll put in the specific value, is equal to minus 155,000 minus let's see, 282,807. That's what this number is. 282,807. And if you add those, you'll get 437,807. That's the present worth of that cash flow. Now we want to do the same thing for B. The present worth of B at rate I equals the initial cost, P again, minus A, P given A, I, N. The initial cost is 210,000. The uniform annual series is 10,000 a year, and P given A 10% for 30 years again. And this will be minus 210,000 minus, and B has a cost. The present worth of this 30 years is minus 94,269, and that will be equal to minus 304,269. So clearly B is much better. You pay a little bit more up front, but you save 20,000 a year for 30 years, and that's has a significant reduction in present value. So that concludes our problem for chapter 4. The next example problem that I'm going to work is from chapter 5. And an investor wants to invest an equal amount at the end of each year from year ages 31 through 60. Well, let's draw a little time diagram here and start here at 31, and there'll be a certain investment amount, 32, and that will go on to time 60. Which is a 30-year period. You know, if we take a look at this, that's 30 years is what this is saying. Such that starting at age 70, okay, so we're going to come out here, he can make withdrawals, guaranteed annual withdrawals of 100,000 a year. So he wants to be able to take out 100,000 starting at age 70, and do that forever. So we'll go to 71, and that will go on out to n equal to infinity. We have this infinite A series, okay, of withdrawals. Okay. He will make no deposits during the years 61 through 70. So there's no deposits coming in during this time frame, okay? Assume an interest rate of 8% per year for all the years. What amount must be invested each year, years 31 through 60? So the question is, how much is this A series? A 31 through 60 equals question mark, dollars per year. So this is a uniform series. The first thing we'll do then is find the present worth of this infinite A series. Well, where will the present worth be? 1 year before the series starts. So it's going to be at year 69. So the present worth at year 69, present worth at 69, at rate I, for this infinite A series, remember the formula was the present worth of an infinite A series is just the amount of the series divided by I. So that's going to be 100,000 divided by I, but I is equal to 8%. I think we had that stated there. There it is. So I should state I 8% per year. So if we divide 100,000 by 0.08, we basically get 1.25 million. That's what the present worth at time 69 must be in order for this $100,000 to be withdrawn forever. Sorry, I'll get that over there. Okay, so now we're going to work backwards. If we know how much we have to have here, we can move this all the way back to time 0, or actually 30 years, by calling it P given F. This is a P, or present worth, relative to this series, but it's a future value relative to time 30. So P at time 30 at rate I is equal to P at time 69, but that's really an F, which is equal to F at time 69. I should have P at time 69, which is equal to F at time 69 times P given F. I'll leave that equal sign there. At rate I and periods. So once we do this, we will have 1,250,000. That's the amount that's here. That's this number. Times, to get it back to here, we get P given F, 8% for how many years now? We're taking it all the way back to time 30. So that's 39 years, not 38, because it's got to be 1 year before that first A payment. So it's not time 31, it's time 30. From 69 to 30 is 39 years. So then we plug in to our trusty app there, and when we do that, we get $62,142. That's amazing, huh? That's the present worth of this A series now. And now I can just convert a P to an A. I know how to do that. A for periods 31 through 60 at rate I is equal to P at time 30. A given P, I, N, is equal to $62,142. A given P, 8% for 30 years. From time 31 through time 60. That's 30 years. So once we do that, we will get A 31 through 60 at 8% is equal to, we crank through that, we get $5,520 per year. Imagine that. If you could just invest that much for those 30 years, you could withdraw $100,000 forever, as long as you can earn 8% per year. That's amazing. The last problem I'm going to work for you is a problem from Chapter 6. Chapter 6 deals with rate of return analysis, and the problem states a manufacturer of software has initial cost of one part of their manufacturing process was $130,000, with an annual cost of $50,000. So the initial cost is $130,000 with an annual cost of $50,000. Let's see how long that goes on. And revenue in year one of 79,000. This is 50,000. This is 79,000. Increasing by 1,000 a year. The revenue is going up. It didn't say anything about the cost going up. So the G is 1,000, and the first payment in that series, or the A series, is 79,000. And that then there's a salvage value of 23,000. There's also a G here, or a cash flow, and then a $23,000 salvage value. And this is at the 8-year mark. Determine, and it says the process is discontinued after 8 years. So that's it. Determine the rate of return the company made on the process. Remember, the rate of return is the interest rate at which the present worth of the net cash flow equals 0. So in order to get a rate of return, you have to have positive and negative cash flows, and we certainly have them here. So I'm going to write the generic equation for rate of return is the present worth at I star, that's the rate of return, that's a special rate of interest, is equal to 0. That's basically the present worth equation. But now we have a lot of things going on here. We have an initial cost, and by the way, time 0 is the only time that there's a net negative cash flow. Again, if we break this positive cash flow series here down, we will get a uniform series of 79,000 and then a gradient series. But then we also have to subtract off the 50,000 from that uniform series. So we will get the present worth at some unknown interest rate equals minus 130,000 times P given, I'm sorry, you don't do that, plus, then you have 79,000 minus 50,000. That's a uniform series right there. That's an A. That's a net A of 29,000, and then you get the G because that's going up. So this is going to be P given A, some rate for 8 years. And then finally you get the G series, G times A given G, I, and N is 8 again. So I'll put the generic number N there. And I could put A revenue minus A cost here. So this will be equal to present worth at I star equals minus 130 plus 29,000 P given A, some unknown rate for 8 years, plus 1,000. I forgot the salvage value, plus 20 S P given F, I, N, we'll have to add it in, P given G, 8%. Okay, it appears that there's, oh no, I'm sorry, unknown I, 8 years, okay? And then we have the salvage value plus 23,000, P given F, I percent, I star, and 8. So everything is, put the I star, dot. Now, the way to get this, if you're not using Excel, you get this directly off of the app, the I value. You could get it from Excel because it has an algorithm that'll work that. But the way I worked it in the videos is to use trial and error. Now, in this problem, if it was on a test, I would have given you a hint, okay, as to where to look to do your trial and error, so to speak. And in this case, the hint would have been I star is greater than 15% and less than 20%. So you have to know that to know where to start, okay? So I'm going to start and try I equal 15%. And when I plug in present worth at 15%, I get minus 130,000 plus, when you plug in 15%, P given A times 29,000, you will get, and you go through all of this, you will end up with, you get this brought down here, and then this brought down here, and then this brought down here. You end up with the present worth at 15%, I'm kind of saving time here, is equal to 20,132. And that's a plus value. That's greater than 0. So I know I star is greater than 15%. And the hint was that it's between 15 and 20, so I'm going to try 20%. Present worth at 20%. And when I do that, I get minus 3,490. That's less than 0, so I star is less than 20%. So it's somewhere between 15 and 20. And the way you work this is it's a ratio and proportion. I think I did this in one of the lecture videos. So I star is equal to, you start with the base 15%, plus then you get the difference in percentages between these two trials. We tried 15%, then we tried 20%. So this would be 20% minus 15%, which is of course 5%. And then you take a ratio and proportion of this distance to the total distance down to here. Okay, so it'd be 20,132 divided by 20,000 minus a minus 3,490, which would be get me to I'm not sure what. It would be, well, let's add these numbers. It'd be 2, because this is a minus, it becomes a plus. And carry to 1 is 6, and 23,622. And it turns out that this is 0.85 times 5, which gets you to 15%. I star equals 15% plus 5% times 0.85, and that gives you to 19.3%. If you actually solve this using Excel, you'll get 19.2% or 19.17, and so it's very close, and that's the answer. That's the rate of return. And this concludes the problem session of working problems similar to the kinds of problems you'll encounter on the exam. Um, all of these problems are similar to end of chapter problems, and many of them are similar to homework problems. Thank you.